Hello, 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 everybody. Let's check if our Zoom colleagues are able to hear us because behind the scenes, we have a Zoom channel that actually everyone is welcome to join. Right, so the stream should be live, and here we are for day 4 CodeRefinery. In these first 10 minutes, we just chit chat. There's Jarno. Hello, Jarno.
Hey.
There's Ina. Hello, Ina.
Hello.
And Thomas.
Hey, hey.
So I still don't see any feedback from our Zoom chat. If you hear us, if you see us, please make some noise. But anyway, so today it's an interesting day. It's maybe, I mean, it sounds, of course, if every time I say this is the most important day of CodeRefinery, it feels a bit, hyperbolic. But maybe this is the most important day of CodeRefinery because it's really the day where we link all together the why are we here and what's the final goal. In this notes document that I'll just share with you via email, there's already some icebreakers. So if you were with us last week, you should be already familiar with this. But if you are just joining for this day, basically you can scroll at the top of the document, of this notes document that I'm sharing. And at the top, there's a pencil. So if you click on the pencil, you can answer these icebreakers. And the first one is interesting. And of course, I'm going to ask our instructors of the day, what do they think of? Have you ever heard the sentence, works on my computer? What does this mean in practice? How do you solve this problem? What about Ina? Have you ever heard it?
Yeah, well, I guess I've heard it, and it was usually just very simple stuff, some missing packages, dependencies. So generally looking at error messages or how the problem presents itself has been easy to solve in my hands, but I think maybe Thomas has some more stories to share.
I just wrote one down. We just yesterday had a user where they had a program, a Python program that is running on several of the machines in the lab, but for some reason doesn't run on his machine. Um, Admittedly, we tried to figure out, we didn't find the final reason, but the assumption that I'm currently working on is, yeah, different environments. So we do know that there are version differences between his machine and another one, and in the end we told him that, yeah, maybe get the environment that's working on the other machine and use it
And
on
they,
your machine.
were you using
See,
conda? Was it a conda environment?
they had an environment. So the installation instructions essentially had an environment, but in that case it was install PyTorch, and the program is from 2023.
I see.
So, well, the PyTorch version that it depends on in the setup is something like 1.10, and we are now at 2.8, and there are quite a bit of changes, and not only there, but yeah, that's a relatively typical situation where, yeah, it works here, it works on different machines, but it doesn't work on mine. Why?
Yeah. We have this internal joke with our team. Thomas, by the way, is part of our team. We have a daily support Zoom session, and we usually have, that conda is mentioned every day. How many days since conda was mentioned during the support? And it's usually 0, which is conda is an important tool. You will hear more about conda today. In general, if you think in your work, I think Ina has been mostly using Python and Thomas a bit of MATLAB, a bit of Python. Have you ever experienced this, that maybe after many months or even more, many years, the same code that used to work stopped working? Was it easier? Was it easy to make it work again, or was it impossible?
Um, yes, I have had that experience. it's very often the problem that yeah, I come back to something old from myself, and depending on how much of a rush I was in when doing that stuff, it's difficult to see what I actually did. And getting back in, like what the user here is writing as well. And the other thing is, yeah, that I particularly recently with what I just mentioned, PyTorch changes, where the library is, or at least has been, now it starts to slowly, well, settle down. But in the beginning, this was changing so rapidly that the library that was working 2 months ago is not working now. So you really had to be careful what versions you were using for what code and things.
And what about Ina? Have you experienced this? How
Yeah,
can I call it? Lack of self-reproducibility.
I think actually not that much in my hands, because I tend to have fairly self-contained code for many of my projects, but working with others, and then especially also working with PyTorch, I have similar experiences. So especially when the versions were in quite a lot of flux and the change between version 1 and 2, that made things interesting, to say the least.
Yeah, I personally had sometimes we need to maybe help somebody to run a tool that came from a paper for a few years back. And I remember once that tool was specifically working with a certain combination of versions. So I had to go back and see in 2021 which NumPy was there and which whatever package was there. I tried to see those numbers, and then in the end we managed to recreate the environment. But it's just sometimes traveling back in time with code, try to reuse code from other paper also require this type of investigation on versions of different packages. And maybe
Yeah.
Python in this sense is one of the, I mean, Python is amazing, but also is one of the worst when it comes to these dependencies and chains. And in a way, MATLAB, you can say anything bad about MATLAB. I've been using MATLAB for many years, but being self-contained, that if I'm using MATLAB, whatever, 2021, I can just tell Thomas I'm using MATLAB 2021. Of course, there can still be
Yeah, okay.
reproducibility issues, but
Okay,
in
yeah,
this sense, you know.
but essentially what you're doing there is you said, I'm using MATLAB 2021. So yes, you have a version number for the software you're using.
Mm,
So you have exactly the same as I'm using Python 3.10 with PyTorch 1.0. That's a clear version definition. If you would say I'm using MATLAB, or I have some MATLAB code, uh, I remember a situation where we were teaching something, and MATLAB decided that they will change the default output of a function to assuming that a parameter is set versus it wasn't assuming that parameter before. So we had examples that were running on, I think it was MATLAB 2018 or something, and in 2019 they changed the default for a parameter, and I was like, why do our scripts no longer work? Um, we, we we are just using MATLAB functionality. They should work. Oh, great. So now we are not getting the full output anymore. We need to add this parameter to get the full output that we got before. So I think
and
all
that's
languages have this
actually
issue.
you were actually in a good scenario that you were able to see that the script were not working. What if the change was so subtle that you know the output
Yeah,
is still similar, but I don't know, maybe the order which things are sorted is different.
well, we noticed that the scripts were the scripts were actually working, but the answers were not the same anymore. Because it was essentially about solving differential equations, and before they gave out parameterized solutions by default, and after the change they didn't. So they gave one solution.
Yeah.
And yeah, that essentially led to, yeah, the script works, but it only shows one of the multiple solutions.
So you kind of got already a feeling of what we're gonna cover today. It's 1 o'clock in Helsinki, Finland. So we can now start with day 4 of the CodeRefinery workshop. Hello everyone and welcome to day 4 of the CodeRefinery workshop September-October 2025. With me today we have Ina Pöhner from University of Eastern Finland and Thomas Fau, Tom from Aalto University. As you can see, I'm sharing the workshop webpage. As usual, this is the reference point for all the links and all the material that we will share today. And today starts a different kind of part of the workshop. We often call it part 2. So then instead of having every day like we had last week and a little bit longer days, the next days are a little bit shorter. And instead of being one after the other, there will be a week. So in practice, for the next 6th or for the next 5 Wednesday and for today, we will start at 1 p.m. Finnish time and whatever is that in your time zone. And the workshop will be more kind of episodes that don't really depend on each other, but they are of course linked all together. And today I'm very happy to talk about, I'm very happy that we are covering this lesson on reproducible research because it's really that it links all the different episodes, whether it's the version control or, you know, how do you work with other people, how do you document your software and so on. So when it comes to the recap of the previous week, so far we learned about version control, you learn all the terms that are used, how to commit, whether you're using the GitHub interface or your favorite editor if you work locally. And also, of course, the most exciting bit of version control is to work with others, fixing other people repositories or accepting changes to your own repository. Now, for this part 2 that is starting, we are going to go more broadly in topics that sometimes maybe don't have practical exercises, but compared to the previous years where this second part was mostly kind of demo based, this year we decided to introduce more exercises, and so hopefully you will have fun today with some interesting reproducibility exercises. When it comes to the notes document, you should already receive this collaborative notes document. And for those who are not familiar with this document, at the very top, now there's our cameras there, but under our webcams, there would be a pencil. And so that if you click the,
There it is.
yeah, okay, now you see that my mouse is on top of the pencil. Now I click the pencil and the interface changes into some sort of like a editor mode, and here everyone can edit. So for example, you could already answer one of these icebreakers, like have you heard this sentence works on my computer? And it's nice to hear your stories of, you know, where this type of computational reproducibility has failed. But I'm still in precious times from our instructors. So I scroll back up and switch to this I, which is the view mode, meaning that I don't need to edit this document anymore. And so I'm very happy that today we have Ina from University of Eastern Finland. She's a researcher working with computational methods for drug discovery. At least this is what I understood. Hope it's correct.
It is.
And Thomas from our team at Aalto, who is a research software engineer, having lots of fun, especially with web development and applications and things like that. So the stage is yours, and I think we should switch to Ina's screen, if I'm correct.
Yes. Okay, thank you very much for the kind introduction, Enrico. And as Enrico mentioned, so we are here today to talk about reproducible research. And as Enrico has also already mentioned, this kind of connects all the different parts of this workshop together. And let's actually start from there, how it all connects. So what I think is pretty clear when we talk about how do we get reproducible results in the end is, well, we need the data. That's pretty straightforward, right? And also, of course, we need the code used to generate the results. But then there is another thing that we need to think about that is called, here are my tools, and that might be a little bit more alien to you on the surface, but we are going to talk about that quite a bit today. So think of tools as all the other things you need to know, all the prerequisites and everything else you need to have in addition to code and data to make reproducible results. And what has this got to do with this workshop altogether? So actually the whole workshop gives you all the tools you need for computational reproducibility from a computational perspective. So this here is my code. Those of you who have been there during the first week or already know version control with Git have a sense of how this can help you. And there's a lot more coming on topics like social coding, so licensing, how to get credit for your code, documentation, Jupyter notebooks, annotated executable code blocks, and automated testing, modular code development. All of this helps you to make your code reproducible. But then what about the other stuff? So this here are my tools is what we are going to cover today. General reproducibility, how you can actually prepare your code and put it in context so others and you can use it again in the future. And what is important, and I want to stress that right at the very beginning of today's lesson, is this might feel a little bit overwhelming. So we are going to cover a lot of ground today, and you might think that maybe I don't really need these things right now, so what am I going to do with this information? And what we really want to stress is we want to show you what's out there. We want to give you an idea how can you achieve different things in case this becomes relevant to you in future, but don't overthink it, don't fret. What we really want to point out is focus on good enough. Start somewhere, start with small steps. That's already a big step for overall reproducibility. Think of one topic maybe we cover today. You can get inspired, perhaps, if you know that you want to submit to a certain journal, then look at the journal requirements or look at your funder requirements or talk with colleagues. Maybe your work group has some requirements that have to do with data structure, reproducibility aspects. So get inspired by something that you need that helps you right now and start with one topic and just try to learn and implement that. And if you don't really know where to start, a great way we find that helps you to identify bottlenecks, problems, missing links is always to just give your code to somebody else, and every question they need to ask you tells you probably something where you could improve a little bit on reproducibility. And now I think based on the icebreaker, this is something you are all here because you already have some idea about reproducibility, and I think at least some of you can quite nicely connect to this PhD comic that you have suffered through the great fun of starting from somebody else's work. Nonetheless, why are we talking about this? So what's the motivation overall behind reproducible science? And we have here a scary anecdote for you. And in fact, this is a true story that we have really seen happen in real life. So it's not just something that we put here to convince you. So imagine this. You're in a group of researchers and you obtain really good results. So obviously you want to submit that work to a high-profile journal. And then a month or two later, reviewers ask you to make some changes, get some additional figures in, do some more analysis. And as you try to implement those changes, you realize that actually there's something odd happening. You can't even quite reproduce the original figures. There seems to be some data missing that you can't find. And you can't really reproduce the results of the original submission. And maybe you don't even know what parameters were used for generating the original data. And this can just mean that the manuscript never sees the light of the day. So it's still left in the drawer. And well, of course, this can be quite bad for you if, for example, your PhD depends on that paper, your next grant, maybe your next job expected that this paper would eventually be published, and now it's not happening. So this is a bad situation that I think we can all agree we want to avoid. But then you could argue, hey, this is just an isolated thing, and obviously this happens to some people, but it's not going to happen to me. And it's not really something that happens very often. And well, some of you might be familiar with this already, but in case you have not seen this quite telltale survey published in Nature now 9 years back about reproducible research, asking researchers across the life sciences, have they ever failed to reproduce an experiment? And now it might not be such a big surprise that quite many failed in reproducing someone else's experiment, but what's a lot more depressing is that you see that almost as many have also failed to actually reproduce their own experiments. So that's rather bad, and it's probably the publication that kind of coined that term that we really accept that, hey, we have a reproducibility crisis. So more than half of the surveyed researchers said, okay, there is a crisis going on in science right now. But this is all from experimental sciences, and what was among the reasons they asked about was that methods and code were simply not available. So then you can't reproduce it. And hopefully, since you're in the CodeRefinery workshop, you already know how to avoid that one and how to do better. And also, as I said, experimental sciences, there can be any number of reasons, but you would naively think we're talking about computational methods today. So this is kind of deterministic. You feed it some data into the same code, you get the same result out. So this should be an easy one for us to solve.
Yeah.
But in practice, well, I can tell you that we have quite recently done a reproducibility study with my team and trying to actually run over 200 published research codes. And it's easily as grim as what you have seen here in the experimental sciences. So a lot of failure cases. Actually, the majority of them had reproducibility problems, more than half at any rate. And top reasons were, for example, complete lack of documentation. So that's something for you to learn more during day 6 of this workshop. And then the other topics were things like environment definition problems, missing dependencies. So a lot of reasons that had not so much to do with the code itself or the data, but actually with that environment, with these additional tools and requirements that we mentioned in the beginning. And hopefully, after today's workshop, what we will teach you helps you to avoid at least some of these pitfalls and do better. And when we think about reproducibility, that's also important to recognize that we often kind of think just about code and data. We might acknowledge that documentation is important, and we might be very focused at this end goal. Okay, we want to write an article, or maybe you have a different end goal. Maybe you just want to publish software, but whatever your end goal is, this rests on top of documentation, code, data. That's all very nice, but it's just not enough. And all of this rests on a foundation that has to do with the environment. And if we don't really know what to do with your code and your data, how these things come together and where you executed them with what other tools in mind, then the whole thing just breaks down. And that's just important to recognize that reproducibility is more than just code and data and documentation, but there is something underneath it that we should also take into account. And yeah, I have now already shared my own experience with trying to reproduce code, and I think we have a couple of interesting stories by now also in the icebreaker questions about your experiences with rerunning codes, adjusting scripts, figuring out what you have done a couple of months ago, continuing to work from somebody else's code. So maybe I think it's time to maybe switch to Thomas's screen to see what interesting stories we have by now in the collaborative notes.
Yeah, overall, the most interesting thing that I saw here is when coming back to their own code, a lot of people are saying that they do need to take a couple of days to get back into what they were actually doing, and I can completely understand that. It's the same for me. Even with good documentation, you just need some time to get into a new project, even if it's a project that you have been working on before. It often code styling, code considerations are somewhat different between different projects, and then it's just, yeah, you need some time to get back in.
So have you ever experienced that if you're looking back at code that you wrote 2-3 years ago, that it feels like it has been written by a different person?
Yes, definitely.
So I think
It's also, especially if you are working in a field where things are evolving, things are changing. You look back at code that you wrote a couple of years back, or even sometimes even a couple of months back, and think like, why the heck did I even do this like that? Because this doesn't, well, yeah, okay, it works, but it's not what it should be. It's not how I recently found style for this kind of library, or how this type of library should be used. And it's very often that as I said, you come from a certain style of writing code, and if a library has a different approach to coding in general, what you write and how you interface with that library might look very, very, very different. And at some point, if you use the library enough, you start to understand how they were thinking, how they want things to be used with this library. And then you start writing your code that way. And then you look back at some old code and you think like, this shouldn't be written like this.
yeah.
It should be written completely differently. And when it comes to continuing work from other people, yeah, I think the first one is quite telling. Was there's a lot of errors coming up. You need to find which versions where to put things, and it's pretty much undocumented. And I think we'll come to the documentation will be in 3 weeks, I think. And documentation is probably also one of the most important bits about code development. And then the problem that if you have really old things, then well, you just can't find the right versions that were used to compile that. Because if you have something from here it's from 2003, you don't necessarily know whether that was compiled with the latest version, or maybe a Linux 3 or 4 years old that didn't have the latest versions and was just about at its end of life. And yeah, it was compiled with something even older and only worked with that. So like Enrico mentioned in the icebreaker time, that is something that very often comes in the way of, reproducing things, either your own or continuing work from others.
Yeah, and I think we have already now talked a lot about the aspect of versions that you don't really know what versions people have been using. And that's, for example, also in our study was a huge problem, that you know when code has been published. But if they don't report the versions, it can like simply mean any number of things. You can roughly guesstimate what package versions were relevant in 23. But then they might have worked with versions, and they might have worked on a project since, let's say, 2018. And they have never changed their environment, so they are using even more outdated versions than you would think. And if there's no information about that, you have no way of knowing.
And there's actually, sorry to interrupt, there's actually one good question here, always whether if a scientific findings depend on the specific version of libraries, if it then is actually reproducible, or if it cannot be repeated with different libraries. And I think this very much plays here as well, because there's two different things. There is the science behind a certain code, that where if this works properly and is not dependent on things like numerics or other non-code based issues, let's phrase like that, then I think it's okay, and it's also reproducible, even if it doesn't work with a newer version, because the new version is essentially a different tool.
Yeah.
So it's the same as if you would say, well, if I have a completely different machine to analyze things, it should still be working. Yeah, but only if that machine actually produces the same kind of outputs and takes the same kind of samples from preparation. So it's really this, if a library changes, sometimes functionality stays the same. But if the functionalities do change, for example, an underlying algorithm for a certain functionality, because someone found that there is a more efficient one for some type of approximation, and now, well, it gives slightly different results because, well, it's an approximation.
It's also, I think, important in this context that we distinguish a little bit between kind of technical reproducibility. So can you even rerun the code in itself? Can you generate output in the first place? And a lot of this versioning is going to break that first rerunability or technical reproducibility. And then it's a whole different matter that depends on other things, and their changes in the libraries, like you just explained.
Yeah.
Can, of course, also affect the results. Can you reproduce the exact output, or at least in reality, when we work with approximations, it's quite often more a question, can you get the ballpark right? So it will not be exactly the same floating point number, but it should at least give you the same general direction and general idea. And that's kind of more the actual reproducibility of the results of a computational study.
Yeah.
But quite often, unfortunately, I can attest to the fact that you fail already in the first step. So you cannot even get this technical reproducible. You cannot run the code. And if you can't run the code, then there's no point in even talking about, would I get the same results with the information I have? Because, well, it's not running. So I hope, since we've talked a lot now about versions, and there, of course, when you work with somebody else's code and you run into a lot of errors, not everything is related to versions and environment, but I think we have heard a couple of examples and seen a couple of comments that link to, for example, venv and conda environments and versions that you install, that kind of tell you that this is very much at the core of the issue, that we simply do not know enough about these tools and about the environment to reproduce code. But before we dive even deeper into that topic, I think let's talk about something that is maybe even easier. And if you don't really know what is the first step, where to start in order to improve reproducibility, then this is a good place for you to begin. And it might seem really obvious, But trust me when I tell you, in practice, sadly, it's quite often not. And start from organizing your projects in a logical fashion, because like we heard in that anecdote in the beginning, it might actually be quite useful to simply know, where are my files? Where are those scripts that I've executed? How does it link to the data and so on? And well, some of the repositories we tested, you look at the code repository and you get this wall of files that are like script 1, script 2, script 3, data 1, 2, 3. Personally, I think this is even for the authors themselves at a point impossible to know what is script 1, 2, 3, 4. And this is actually a really low-hanging fruit, that if you just structure your projects cleverly and you name things in a reasonable way that is descriptive, that's already documentation in itself. And it kind of really becomes natural to you after some time that you structure projects in a different way. It becomes normal, and then it's not really that much effort anymore. And we just want to share with you some ideas on that topic. What is a directory structure that people have really found to work for that kind of project basis? So for example, that you collect all the project related files, at least what you have related to a certain project, if you're just working in a multidisciplinary project on, let's say, computational part, then collect all the data you have in a single directory and put different projects to live in their own directory. And then, as I said, try to use the naming to already give you a hint, what am I actually looking at here? So not script 1, 2, 3, but actually tell what the script is doing. And yeah, this is maybe, I think we are mostly Linux people, so we hate spaces in file names and directory names. But generally, it's a good idea to avoid spaces on other systems as well. Use dashes, use underscore or camel case if you prefer. It's just nicer to work with, and there's no ambiguity what's like really the full path, and you don't have to worry about escaping spaces and other things like that. And if you need, let's say you actually work with some personalized data, sensitive data, then of course you should have private directories where it's really clear that this is something you don't want to share with the outside world. And at least those of you who have been there in week 1 have heard of that git ignore. So just if you need a refresher, you can check the lessons during the first week. But this is basically a file that tells you when you version control that whole structure, this is the stuff you want Git to ignore. So this is not going to be put anywhere. And then have README files. So have a README for the whole project that describes what is this project about, what do I have in here. And then also have a README file, for example, for the data. There, log where did the data come from? When did you get the data? Especially when you get data online, the data might change, so also put timestamp information there and pull the data down into specific subdirectories, and then you will always know exactly what version of the data you used. If you manipulate data throughout your pipeline, then create another folder. Have a separate folder for all the intermediate files. That helps you if something goes wrong, or if you later on need to track what has maybe changed in my data processing code, then you can actually compare the first intermediate files with the second ones and get some idea, is this a problem, for instance. Then have a folder for your final results where you put things like your final data, your tables, your figures. Maybe you want to have a folder for the manuscript describing those results. And you want to have a documentation of the whole project. And inside all of this, you have your source folder where all your code lives, with a license ideally, and the requirements or dependencies. We are going to talk a little bit more about requirements and dependencies today, and you can learn a bit more about licensing, I think, next week in the social coding session. But anyway, this just is already a project structure that is very much self-explanatory and that would help you to avoid a lot of the problems we have mentioned in that scary anecdote in the beginning. So if you consistently followed that kind of project structure, you probably won't end up in a situation where you don't know where is the data, what parameters were used, or simply you can't really trace how did you get to the intermediate files, and you have a chance to rescue your manuscript. And now you can really track what is inside your source folder. You can, in principle, within some limits, also track your data if it's not very big. If it's sensitive or large, then again, untrack it with git ignore. Keep all the intermediate files and consider those git tags to mark specific versions. So for example, if you have something that is related to your thesis, to your manuscript, or a poster presentation, then you can use the git tag so you know exactly, okay, this is the status when I generated that poster. And that can be really helpful. And there are even a bunch of templates that you are welcome to try for R and Python. We have some examples and some more general guidelines and many more in this blog that can help you with some ideas how to structure things, with what components to put and where. And these are really great starting points if you don't quite know how to best organize things. One small request though, please remember to actually populate it. Do not just copy a template and then forget to write actual documentation about your code, because we also had a repository where I was thrilled to see, hey, this has everything. Documentation, all the intermediate files, that whole structure I have shown to you. And when I looked into the data structure, there was just nothing. So the documentation said, okay, enter your documentation here. So thanks very much. All of this is nice and gives you a guidance what you need to fill and where you need to fill it, but just please remember that it won't autofill. We will give you some tools throughout the workshop that help you to make this easier, but still it requires some input from your side to really write specific documentation for your project and populate that with information that you actually need. And this is also something that should grow kind of organically as your project progresses. You have to also remember to update the documentation. And it might seem like a lot of hassle at times, but I think it's an important step to avoid such things like you basically can't publish a manuscript because you have lost track of what you were doing somewhere along the way. And the more often and consistently you are doing this, the more natural it becomes. And it's not really a hassle when you do it the 5th or 6th or 7th time. At some point, it's just natural. So hopefully we will give you all the tools to just get you started along that line. And I think the bottom line of all of this is a good structure can be a very important part of documentation in its own right, and it's a fairly easy thing to do and usually quite applicable to any number of projects. So if you don't know where else to start, this is maybe where we would recommend you just get going, because this is going to really have a huge contribution to reproducibility. And especially then if you're in a larger collaborative project, you know where to find things if you get reviewer comments, and you can also help others to find things in your own structure more easily. And yeah, speaking of collaboration, I think now let's take a quick excursion to talk about collaborative writing of academic papers. So now we have covered a bit of the bottom of this pyramid, and we have talked a lot about versions, directory structure, how this is a bit of documentation, where to put data, where to put code, and then we have this final top of the pyramid, the article. So what are your experiences? How do you collaborate on writing academic papers? How do you handle issues like conflicting changes? Maybe Thomas, can you share some of the stories and experiences in writing papers with us?
So also from the notes here, I've personally done two of the three approaches that I of the four approaches that three that are mentioned in the notes now. I have done the drafting things on Google Docs and doing a final submission, then putting it into LaTeX. So taking the templates that that journal is offering, because if you need to write this to some other journal, you will have to fill it into their template again anyway. So having draft where you just have text that you can just put into certain places and notes like figure here, makes it easier to do these kind of adaptions. I've also done the overleaf approach where multiple people were working on it, but that was mainly working because it was primarily computer scientists that were accustomed to LaTeX. So everyone was on the LaTeX thing. And I have had the unfortunate pleasure to have Word documents sent around and edited, and version X, final version 1, final version 17, final version 17 v2, final version 17, your initials, their initials, whatever. So yeah.
Yeah, I can share a fun story on that too. So Word documents sent around via email. I was not carbon copied on several of those emails. Then I was asked to revise the manuscript, and I did. Then I got a very angry email by the first author saying, "Hey, but you used the wrong version." And I was like, "I used the latest version I had." And then it turned out that they actually sent another 2 versions around that I never got. So this is just unpleasant. And I think one important motivation, because this kind of goes into version control, and why also we suggest to think about version control maybe for manuscripts, and to try to have it somewhere there everybody can see what is really the latest version, to avoid those kind of problems. But also, this has also been, I think, published in Nature a while back, that somebody wrote that they used version control and basically Git mainly to show that their manuscript was not written by AI. And this is now something that I think becomes more timely and relevant every day, that it's not a bad idea if you can kind of show how your manuscript, how your text evolved over time. So you avoid that reviewers say, "Hey, obviously this just came at the click of a button from ChatGPT." So another thing simply to keep in mind, that having version control, having a protocol that really shows when and how things changed, can also help you to fend off such nasty reviewer comments and suspicions a bit.
I think what I would in general recommend from personal experience is we have nowadays the option to have collaborative documents where multiple people can edit and comment on. And I think one should make use of these tools. The times of sending around version drafts should be over, in my opinion, because that's to me the worst possible option, because you end up exactly what you said. Someone gets dropped from an email chain, works on an old version where all the typos have already been fixed, and the next one sends their comments, and then someone has to try to compile the things, and it's just a complete mess. So please, this is kind of, don't do this. Do something else. Do some collaborative document. Personally, I'm not that big of a fan of using Git for version controlling a paper, at least not for version controlling the process of the actual process of writing. Maybe for some revisions, but for the writing process, I'm not that big of a fan because you end up with exactly the second question that we have here, where you have multiple people working on the document and submitting, and then you get merge conflicts, or well, if you're unlucky, you get merge conflicts. If you're lucky, you don't get merge conflicts, but you might end up with two people writing the same kind of comment that needs to be added to some paragraph, and they write it at slightly different places, and then you have it in twice because yeah, it merges nicely. It doesn't complain with a rebase or something, and then you notice it somewhere sometime later, or you unfortunately don't notice it at all and submit something that feels like, oh, why is this mentioned twice? And reviewers getting annoyed. So that's where I personally would prefer or would recommend using a collaborative editor nowadays
Yeah.
because they are available and make use of the tech.
Yeah, and I think, I mean, Word is still, at least in our field, unfortunately, very, very common, and people have a certain resilience to changing. But I have to say that I've been with LaTeX for quite some time. Also, Overleaf a while back did not have the functionalities that you would find in Word, but now it does. So the argument that, for example, you can't use LaTeX with people who don't know how to write LaTeX, I have had a couple of people who really have never used LaTeX before working fine with Overleaf. You can write comments, you have track changes, so all of these things, I think, also in typist, if you prefer Markdown, these tools are there. So the argument that people love to give for having to use Word, that you can't comment on the files or you don't see track changes, that just doesn't apply anymore. And then all of these tools also provide Git integrations that help at least with some of these things. So you work together on one document, but then you commit versions on a regular basis. That just shows the track record.
And even if you have to work with Word, you can use something like SharePoint or some other central source. Just avoid having to send around manuscripts.
And yes, I think with that, maybe one other thing, as a little teaser, there's going to be a whole session dedicated to Jupyter notebooks that tells you a lot more about that. But if you really want to have essentially an executable manuscript where you write things in Markdown and then you have code blocks embedded into the manuscript, there are now also tools available where you can basically run those online directly without actually having to install anything. So reviewers can really go read the manuscript and execute the code as they go. So there's a lot of things happening that are interesting in this context of making things reproducible, making collaboration easier, that I think are worth being aware of and trying out if you haven't. There's also some additional reading material if you're interested. But yeah, I think with that we're about done with that first part of our workshop for today. And I think the key take-home message at this point is that if you have an organized project directory structure, that's already a huge step towards reproducibility. And although it might seem obvious, I think also a note to myself that I'm sometimes sloppy in how I organize my projects, and it tends to backfire. So this is the first step to work on that doesn't really require any tools, requires a bit of effort, but it becomes quite natural, quite fast, and really helps a ton. And yeah, also think about version control for the future when writing your manuscripts. And now, Thomas, I don't know, shall we do a short break now, or do you want to actually
I would say let's do a short break now for 10 minutes and then, or Enrico, was the timing that we go for lunch soonish, or?
We can have a break now.
Okay, then let's do a 10-minute break now.
Right, so
Meet back at 5 to the hour.
10-minute break. See you in 10 minutes, and then we will hear some more about directory structures, computational steps, dependencies, and lots of other fun things. So, bye.
And welcome back. So we have talked a bit about the upper parts of the pyramid that we've shown earlier, and now we are starting to get further down this pyramid. After having talked a bit about the structure, now if you have a project that you have something that you need to do, like having a workflow, this is something that also needs to be reported, and very often this is reported in scripts, but it can also be reported in other ways. And depending on what you have, it's like or more easily or more difficult to reproduce. So there are commonly a couple of steps from input data that you have from experiments or from other sources to the results that you want to present for a paper. And we are using a example project that is essentially just word counting. And even in this very simple thing where we want to count words and create some statistics for the amount of words that are occurring in some books, it has a couple of steps. So we first have to analyze the frequencies of the words. That's done in a count.py file. For all the books that we currently have, which is in this data directory. So data directory currently contains these four books, and the books essentially just contain the plain text of these books that we are investigating here. And the counted.py file simply says, yeah, we are checking how often does a certain word occur in this book. And then we want to plot them and generate these nice plots so that we can put into our paper. And for a single book, this is essentially what we would be doing. So I have this in here. I'm creating this count.py, and then I have a IELTS.data that I can have a look at. How does this look like? So yeah, this is the off and O and to, and then I can plot this relatively easily and can get a file that is essentially showing this plot. Let's see. My machine being slow, but yeah, I get this file, and this is all nice and well. But now, if we imagine that we have to repeat this multiple times, that would essentially happen in our run all, which is a script that essentially just says, okay, for the first file, for the second file, for the third file, for the fourth file. And yeah, this works for the 4 books that we have, but if you want to have 500 books now, this script becomes essentially unmaintainable because there are so many different files now, and there is so likely to be some kind of typo or whatever. We can, of course, create this file automatically and stuff, but it's just getting more and more crowded.
I think maybe one thing is that quite many people would actually execute those steps manually, then it's very easy to forget something. So already the script is one step towards a certain degree of reproducibility that I think is important to recognize here, that having a script that makes sure that it's actually executed in order for everything is not a bad thing per se. That's already a good starting point. So
yeah.
better than doing it by hand and forgetting half of the books, especially if you get 500.
Yeah, that definitely. But it just, even if you do it in the script, it becomes unmaintainable. So this is something that you can do for a few things, and for a quite simplistic workflow where you have some fixed input data and some fixed output data, that's okay. That's perfectly fine. But as soon as you start to, for example, collect more and more data over time, and you need to run this again and again and again for new things that are coming in, you commonly don't want to run everything again because, yeah, in this case, the computation takes a second or something. But let's assume that each calculation here or each individual data entry takes an hour or two. You don't want to rerun this all the time if nothing has changed. And one more thing to mention here is that this kind of stating every individual element is also called imperative style, where you tell a script every single thing that it has to do one after another. And well, there are some advantages to this solution compared to processing all one by one. And yeah, as Ninas already mentioned, this run all is better reproducible because you're not forgetting one or the other. So having this in a script, yeah, is the first step. But as I said, if we have more and more things coming in, then there start to be more and more problems. And that's where workflow tools come in. So workflow tools are essentially tools that help you to organize workflows that you have to do in a repetitive fashion or that are more complex. And we will focus here on Snakemake, but there are multiple different other tools that are also mentioned later on. And Snakemake, in contrast to this imperative style, uses something that's called a declarative style. Sorry. And this will also be the exercise, will also be used in the exercise that you're going to be doing soonish. But I quickly go over how this Snakemake or how Snakemake works. So in Snakemake, you define rules, and Snakemake tries to satisfy all rules. And that means that a rule, to satisfy a rule, all the inputs of the rule have to be created or satisfied. And in our book case, the one rule to rule them all, that is essentially indicating, okay, this is the final rule, or this is the target, requires as inputs. You could also call inputs requirements for this, that everything in statistics book data exists, and the book here will be replaced by whatever is in the data array. So this is somewhat of a Pythonic syntax, and you can use Python code in these Snake files. And this data is generated by looking through the data folder, through everything that matches this placeholder.txt, and then saying, okay, this is this becomes the data book, or no, this is the book field of this, and this glob wildcards generates these book fields for the for all elements in here. So for the rule all, we want everything in the statistics book data to exist, and we want everything in the book PNG to exist, and they have to be as recent as any requirements or in each rule, it will be checked whether there have been updates in the inputs, and then the rule has to be executed. And for example, count words here requires as an input the count.py, so your script file. So if you change your script, you will have to rerun this for all elements, and it requires the different book files. So if one of the book files changes, or or there's a new book file, then it has to generate this for the new book file. And the output from this is defined as this is the statistics file data. So this essentially satisfies this input. And so it will look up in the underlying rules what rules could satisfy one of my inputs or one of my requirements. And then there is the command that is being called when this rule is being executed. And that's essentially just, in this case, a Python command. This could be anything else. This could also be R, MATLAB, or whatever language you want. Snakemake doesn't make a difference here. And it essentially says, okay, well, for each input, the input.script value is being used, and that's the code count.py, and the input.book, that's the data, whatever the file is that came from the that again comes from the requirement here, and is passed kind of downwards, and this generates the output, which is again for each file. And this is how Snakemake builds these rules and goes through the graph and essentially checks for every input if it changed, and then generates the outputs, and will also check whether the outputs changed if there are dependencies, because the make plot then depends on the outputs of the count words and so on.
Yeah,
So
I think this is gonna be maybe easier and more clear once people have gone through the exercises
yeah.
too.
So there are two different options how you can do this. You can do this on your own computer if you have the conda, if they have the CodeRefinery conda environment. Then just conda activate CodeRefinery, and everything you need will be in there. And then you can go through the exercise on your own machine, or you can do this on Binder, where there's a Binder link on the repository. And if you launch it in Binder, you get a online machine that essentially gives you the same infrastructure that would be available with the conda environment. There's a small difference between Binder and your local machine in that due to the way how Binder works, some files might need to be reproduced more often. Because I think because of indexing, if I remember that right, that is essentially.
I think it caches some files, and then it will also update the cache. So you will not get the counts you would maybe expect, because there are additional files in the background changing. But
Okay, but you have 15 minutes for this. Essentially, go through all the steps in the workflow here, and report on whatever errors you encounter, and see you at 23. Bye. And welcome back. So there were a couple of questions as to why we are doing this, and I will demonstrate a few commands that hopefully explain why Snakemake or any workflow manager can be a useful tool. So I've cleaned up my repository here. There's nothing in statistics. There's nothing in the plots. So at the moment, I'm essentially in just having the data. So if I now run the Snakemake command -j just to say, okay, well, use one core, I don't want to do this parallel, it will run this, and it will run seeing that, okay, there needs to be things done, and it tells you, okay, things need to be updated because they are missing. And now I do have in the statistics, all of my statistics, and in the plots, I have all my plots generated. Now, the nice thing with Snakemake is that we can now, for example, if I take, let's say, one of the input files and just copy it over into, so I just create a copy of it. Assume this is a new book that comes in. If I now run Snakemake again, it will say, okay, well, I'm looking in here. There is overall one thing to do with all. There's one count word that needs to be done and one make plot that needs to be done. And everything else is already done. So it's only doing the thing once. While if I look back what happened before, it's a lot of things. So there's one time the rule all needs to be done. Well, yeah, it's the final rule, so it only executes once. And 4 times it needs to count words, and 4 times it needs to make plots. So at this point, I now looking into the plots, I have a Sierra2.png. If, for example, some of my input data changes, let's take the abyss.txt and remove the people. And I run Snakemake again. It'll say, oh, something changed. And it's the abyss that has changed. And that needs to be updated. So it updates only the abyss. And that is kind of the power of these tools, that you can run them again and again and again, and they will only do what is necessary to be done. They will not repeat things that are already done. If you have, for example, a quite long-lasting pre-processing step that is data independent, but that you need to do, you can have that as a prerequisite in your rules. And as long as the code that's generating this pre-processing doesn't change, so if you have that separated into its own file, you can run this again, and it will know that, okay, well, the pre-processing file that generates my pre-processing data hasn't changed, so I can run everything else. But if my pre-processing data has changed, then I need to run everything else because the dependencies of all the other rules have changed. And that's what's making these Snakemake or general workflow managers so powerful, that they take away you needing to remember, okay, what have I already done? And what new data do I have to now run my things on? And you can keep all of the data in one folder, and if they are separated by file name, it will it's able to essentially go through all the files in there and do something for all the files. You can also visualize how it's essentially doing these things, and the command for that, whoops, that was not what I wanted to do. And the command for that is outlined here. So we create the direct acyclic graph, I think, and put it into a image. And this also shows you how the different rules that it will execute are built. So in our case, all depends on both the statistics and the make plot. The make plot depends on the statistics and then feeds into all. So we have a double dependency. We could essentially remove the statistics from the all rule, and it would still do the same steps because it looks back, okay, this depends on this, and would redo the things. And one question is, why do we use Snakemake for this and not a different workflow manager? And the main reason is it has a relatively gentle learning curve. Yeah, it is something where you need to get your head around how the rules are being generated, but that's the typical different style of coding essentially, and you just need to get your head around, okay, this is how it works. Inputs are essentially the requirements, outputs are the products of each rule, and the rules are somewhat the functions that are being called in some way, and so on. And the all function, I think Ina told me once that she compares that somewhat with the main function of a program. That
yeah, it's not really a function, I agree to that, but if you sort of think of this as where it tells all the other things it needs to execute, that is kind of where this analogy came from.
Yeah, but I think it helps in understanding how Snakemake builds these things. And the second thing is Snakemake is free and open source, so it also installs pretty easily via conda or via pip and can be used cross-platform. There are several things in Snakemake that allow you to run things in parallel, which can become quite convenient on high-performance computing systems, because Snakemake also has built-in support for example, Slurm queue management, where it can essentially run large workflows as individual Slurm jobs. It will submit the jobs. They will run on the cluster, and it will then continue where the jobs left off essentially. It's also possible to do individual steps in individual environments by essentially just adding conda environment.yaml, so indicating this is the environment that is necessary for this, or this is the environment YAML, and it will create these environments if necessary. And that's quite important, for example, as we mentioned very early, with things like PyTorch. If you have multiple different tools that depend on different PyTorch versions, but you want to chain them because the one does something that you want in your workflow, and the other one does also something that you want in your workflow, you can't run them in the same environment. So by using Snakemake, you essentially separate them into different environments, and you can run them again. It's also possible to directly use Docker obtainer containers by indicating, okay, which container to use for a certain rule, and then this will be executed within this container. So it's very flexible and has support for a lot of high-performance computing or things that you need in a high-performance computing system environment. It's also quite heavily used in bioinformatics, but it is completely general. You can write any workflow into a Snakemake file, and it's just making it quite nice to use. And as mentioned, these tools like Snakemake help a lot with reproducibility, because they help you in not forgetting to add certain things, not forgetting to rerun something. And if you essentially run your Snakemake file at the end of your or before you want to submit, and you have defined your Snakemake file correctly, i.e. you also have the script files as inputs and so on, you will run the right code for your data with the right data that's now there, and you can be sure that, okay, I know what I was running on when I built this. This does not help against you running it, then modifying things, then running it again, and having done something with intermediary results. That's where the structure, the project structure, comes back in a bit. Where, okay, if you have something like or general versioning, if I have something at submission version, I should make sure that I know this is the data at submission version, this is the code at submission version, and so that I can rebuild this. So it doesn't help you against that, but it helps you to keep the data in itself, or the data and the results in itself, consistent.
And I think for this version tracking, just to mention that again, really Git tags are quite useful. So you can just make sure, okay, this is the script version, data version, and so on that you use to submit, and then there's no ambiguity.
Yep. Okay, yeah, there are of course a lot of similar tools like Make, Nextflow, CWL. I think it's sometimes interesting to see Make here, because most people know that Make is a tool that is being used for compiling C or C++ code or or Fortran code, and don't really think of this as a workflow manager. But in the end, it has the same structure as a Snakemake file. It has rules, and rules can depend on other rules, and it just executes these rules. So in the end, it is exactly the same thing. But yeah, let's go on from having recorded the flow of how you execute your code, how the different steps in your code are being executed one after another, to what's necessary to be able to actually run your code, and that is dependencies. And we have talked about this already quite a bit, that version numbers are important and versioning is quite important. And I like this image here from XKCD, where you can, and it's very, very true. You have a lot of programming infrastructure, a lot of code infrastructure for a lot of systems. And there are always some small libraries somewhere that are maintained by maybe a person or two in their spare time, and that are underlying a lot of things. And I want to give an anecdote that is from 2024, where essentially exactly this thing almost brought this whole thing down collapsing, and that's the XC story. XC is a small zipping library where essentially it's just about compressing some data. But this library is very, very basic, or very, very much below a lot of operating system code and so on. And in 2024, someone, after a couple of years, had managed to social engineer themselves into a maintainer position on the project and added a backdoor. Quite sophisticated, and it was essentially very, very short before coming into a lot of major Linux distributions, until someone noticed a timing increase of, I think, a couple of milliseconds for some requests that they were doing, and started investigating and found that, oh yeah, there's now a backdoor in there. So yeah, we have this situation. This is not artificial. This is exactly what we have. We have exactly this situation, and it's so easy, even for a relatively simple project like a PhD project, to depend on some things that might or might not be maintained, and that exists somewhere and needs some software. Yeah.
And I think also what I realized is quite often, at least with Python, that some of my students, without even thinking, they find that there is a module that can do the job. And without thinking twice, they will just pip install the module, then another module, and then they have 15 modules to do very simple things that would be there in base Python, and that's okay on some level. But they don't really think that every module creates dependencies of their own, and that sometimes you kind of engineer a dependency hell into your own code by installing those things without thinking about the potential consequences. And sometimes it's a good idea to think about exactly that everything you depend on has dependencies in their own right, and it's just, it can spiral out of control. So it is just something that we should keep in the back of our heads when we install someone else's code, that we do not necessarily know how is this maintained and what does it build on in it.
Overall, I would say it's a general good principle to try to minimize your dependencies, but at the same time, don't try to reinvent the wheel. Have it in a balance. If there's complex stuff that a library does really well, take that library. However, if there is a relatively simple thing that, oh yeah, there is a convenient function in this huge, I don't know, there is a convenient function in PyTorch for my small, I need to flip some matrix or something. don't install PyTorch to flip the matrix. Either do it yourself or use some other smaller library that does the same thing.
Yeah. I mean, we don't want to discourage anyone from using other people's code. It's just, I in my experience,
keep it in a balance.
Exactly, it's just something people don't necessarily think about, and it can be a good idea to just be mindful of those things. That's what I just wanted to say.
Yeah, but to make this whole what are dependencies and so on a bit more obvious, we have this kitchen analogy, where essentially the software that you're running or that you have been writing, that's essentially the recipe for what needs to be done. The data that your software uses are the ingredients, and the libraries are the pots and tools that are necessary to actually do the processing. And that's something that's very often forgotten. How many recipes do you see that mention a pot and a pan as requirements for them? Yeah, well, if you just buy the stuff and you don't have a pot and a pan, you will probably not be able to run this or do this recipe. And it's the same with a computer. If you don't mention this library and this library, then yeah, you have some code, but it requires things that we don't know about. And we often use these tools from others, and that's perfectly fine. But we just have to remember that they are being used. And if we want someone else to use our code, they need to know what they have to use. So there's the idea of dependency and environment management. And tools like conda, pip, virtualenv, pipenv, and so on, they all record dependencies in different files, like the old, like requirements.txt for pip or environment.yamls for conda, mamba, and so on. And they try to solve a problem that you need to define a specific set of dependencies for your project. So listing everything that is actually necessary for your project. The tools then aim to, and that's done in the requirements.txt or environment.yaml. The tools then try to automate installing these dependencies based on the file that you have provided, or based on the dependency file you have provided. They also often do record versions for all dependencies if they install them themselves. And one more very, very useful thing with having these environments is you can isolate environments. So if you have a project that uses packages A, B, and C, you can have those run in one environment, and you can have a project that needs D, E, and F in a different environment. And while if they are completely separate, you could probably run them in the same environment. You might get in a situation where for project A, you need A, B, and C at version 5. And for the second project, you need C at version 7 and D and E and F. And then you can't use them at the same time anymore. You would essentially need to uninstall and reinstall system packages all the time just to have your two different projects still running. Yeah, and having these environment or requirements file also allows you to essentially list things for others, so that you can more easily share the package and share the code and share what you have done and what you are using. And one more thing that I think is quite useful, if you have recorded these environments and you at some point want to try out, let's say a pip package that you found that, oh, that sounds very promising, and you install it and it changes 5 versions because pip says, okay, well, you will now want to install this package. I will make sure that this package works, and at the same time, pip at least doesn't care about whether it breaks some other things. and then suddenly your code doesn't work anymore. And it's sometimes very difficult to figure out what exactly went wrong. So having this environment file that you know is working allows you to just say, okay, well, I'll delete that environment, I recreate it, and I have my stuff working again. So we'll give you what was it? I think 10 minutes again to go through the time capsule exercise here, which is essentially to be answered in the collaborative document, and having a look at and allowing you to have a look at the different types of projects that you can see. And I think we have talked about quite a bit of this already. So hopefully this is not will not be taking too long. But I think yeah, should we give 5 or 10?
Yeah, maybe. Let's start with 10 minutes and people
Okay,
can tell
let's
how
start
it
with
goes.
Yep. So see you back at 55. Welcome back. So yeah, we have seen quite a few people marking down the right comments to the different types of what can be found in the repositories, and I think we can all agree that A is pretty useless. B might be difficult to recreate the software. Maybe we at least know what kind of libraries there are, but we have no idea what versions were being used and so on. C is already a bit better in that it at least gives for some of the things a bit more. Well, it gives the file that you can actually get the data from, but it still lacks the versions. And master is nothing that's stable. D has stable links. Main issue is, yeah, Git repositories can disappear if someone decides that I don't want this anymore. Then it can become, well, obsolete and can't be found anymore. But at the same time, the same can also happen with a conda package. It's a question. These two are, in my opinion, pretty much same quality. It's a bit probably from ease of use preferable if you have the information that they are on conda already, because the dependency resolution is better if they are on conda, but sometimes the code just isn't on the on conda repositories. I will go over the time capsule for the future thing here myself and not have it as an exercise. So if we have an environment, we can create an environment, or if we have an environment file, for example, a myenv.yaml. No, come on. And I think I just called it ML, but luckily it doesn't matter what file name I give it. I can create an environment quite easily by saying, okay, well, I want to create this environment based on my.yaml, and it does matter. Okay. It does care about what the file extension is. And I created the environment already. That I shouldn't have done. But let's rename that. So now it will be my env2, and it will essentially create that environment, and then I will have these dependencies listed there. Of course, these dependencies don't help me a lot because at least if I get this from a project, I don't know which NumPy version, I don't know which pandas version, I don't know which Seaborn version. And this is quite inconvenient. Come on. Taking a bit longer today. Okay, we'll cancel that and just use the one that I already have, which is my env. So I can create that or can enter it. And what I can do then is I can export the environment. And if I do that and look into the environment file that I have now created, it lists a lot of things. And that is all things that were installed by Conda with the version and the build version. And the problem with this is something that build versions are sometimes machine dependent. That can be, for example, some might work on Linux, some might work on Windows. That can be that they are GPU specific, or they are, well, or you have a library that can use GPUs or doesn't use GPUs, and depending on whether it finds a GPU, it will install the one or the other. So this can be a bit too much detail. It's great to provide in your final in your final repository as a this was the environment that was being used, so that anyone who wants to reproduce this, they can know exactly what builds were being used for running your code. And I would personally recommend to have a full export available. But what's for installation often more convenient is something like the from history. And this essentially creates a file that just contains what you originally installed. So all dependencies below that is something that it will pull independently. One more thing that's not in the notes, but that is relatively recent. You can also do a so-called no builds export. Oops, well, it went into from history now, which is the same as the first one, except that it doesn't contain the builds. This is a lot more easy to install because it does not have operating system dependent things, which wouldn't install on a different operating system. But it can still have things that are a bit tricky because it can still have things that are somewhat operating system dependent. So it might still be too precise because for some things you need underlying operating system things, operating system libraries that, yeah, are just not part of conda or of one of these package managers. And for example, pip assumes that all system dependencies are provided by the system. It doesn't care about this. While conda has a bunch of more system-like libraries that it also ships into the environments. And this is also where we can now step into the next area in this lecture, where it's essentially about shipping your whole operating system, i.e., well, containers. And well, there's this meme where, and we had it in the beginning, it works on my machine. Well, then ship your machine. And that is somewhat how Docker and containers were born. Because it sounds nice to ship a machine, but you can't always just take a computer and, yeah, okay, I'll just take that computer somewhere else. No, it doesn't work. However, what does work is, depending, again, a bit on the operating system and on things, to encapsulate as much as possible of a computer into essentially a kind of virtual machine, and then run a simulated machine in the machine. And containers are a small step above that. They are not creating a whole simulated environment, but they are creating a largely simulated environment where you have all the system level dependencies in this container. And to come back to our kitchen analogy, so our codes and scripts, we said, are the cooking recipes. And if we go for containers, we have container definition files that essentially define what is in a container. What does the container contain? And they are somewhat like blueprints on how to build the kitchen. So what things need, what plugs need to be there, what kind of appliances need to be there, and so on. Then you have the container images, and those are essentially showroom kitchens, similar to the built based on these definition files. So built based on the blueprints, you have built a showroom kitchen on its own, but it's not connected to anything. It's just standing there. The sinks are not connected to the water supply and so on. And when you then start the container, you're taking one of these images and you're starting to plug in the different cables and different pipes so that your kitchen actually works. And yeah, you can have a look at these example kitchens and think about what operating systems they might represent. So if we talk about containers, we always go from these definition files that just indicate, okay, this is in there, to the actual container that's being run. And containers and can be built to essentially bundle all necessary tools and ingredients. So they can even also the ingredients. So even you can even bundle the data into your container if you really want to. It blows up the container size-wise if your data is large, but you can do that. And the advantage then is that you have a stable thing that you can say, okay, you can take this and you can run it, and it should produce the same thing that it produced locally for me, because it contains everything. And a container and the image is then essentially this thing that you hand over to someone else, and it contains essentially everything. And when you run it, you put kind of an additional layer on top of that, similar where you can make modifications. But if you shut down the running container, this layer gets removed and you are back at the image essentially. And the definition files are then the text files that define a series of instructions on how to build the container images. And where and how can you use these containers? Well, they are mainly used for two different purposes. One is software installations that are tricky. For example, some database systems or similar things where it's just difficult to install them because they need administrative privileges and so on, and depending on the system, you just don't have them, and you still want to use it. So having something that allows you to plug that in and to still run it can be very handy. Or if it's just a very complicated installation where you need a lot of difficult to obtain libraries that are necessary to run this. What I can also imagine is something where, there is code from way back, and it's a lot easier to build a container that can run the code than starting to write instructions on how to run it. Because when you write these instructions, you can essentially take a container definition file, write these instructions inside the container definition file, and then you have the tool working. And if you provide them the container, you just have the tool working, and you don't need to install them anymore. And it's also making sure that this is encapsulated. This is not doing stuff with your operating system. So if I install a database via a container, it's not modifying my system, and I'm not after shutting it down and restarting my computer, I don't suddenly have a certain database running on my computer because if I had it containerized, it was just running in that container. And if that container shut down, the database is not active and cannot be accessed from the outside anymore. So how do these container recipes or reference files look? This is an example for a Singularity definition file. Singularity can use Docker images, but you have to define that, okay, this is coming from Docker, and this is using the image for Ubuntu 24.04. And then when I have this image, I want to do some installations, some instructions that need to be done. And in this case, it wants to update the package cache and then install Fortune, Cowsay, and lolcat. Yeah, this is pretty useless container image, but it's just for explaining how the things work. You could have anything else that you want to install here. You could do compilations of code that you have in there, and you can also, by having a files field, you can also copy files over from your operating system into the container. And then, for example, compile them and run and have them as a compiled program. You can set environment variables based on in this environment field, and then you define what this container should do when it's being used. And in this case, it would use Fortune to pipe it into Cowsay to pipe it into lolcat, which is more of a joke than anything useful. However, there are definitely more useful containers than this, and we'll come to one of them a little bit later. So what are the pros and cons of containers in general? The pro is definitely that you can move workflows across different platforms. That being said, there's one caveat here. At the moment, it's mostly you can move Linux workflows to other platforms. I haven't really seen Windows containers there because I think the problem is that the container softwares don't really support Windows containers mostly, or Mac containers for that. It can solve the works on my machine situation because you essentially, somewhat ship your machine. It allows for a more stable future reproducibility because if you have created the container and you can provide the container to someone else, they can reproduce it because it has the software, it has everything in there. It's not, this software is not available anymore because, it is available, it is in the container. It doesn't need to be available. Note here that I'm talking about the images. So if they have been stored somewhere. If you only have the container definition file, you're in the same. You're again at the same point where this can change versions and so on. You can potentially use it to send your computer to the data when the data set is either too large or cannot be transferred for legal reasons, like it needs to be in a highly secure environment, and then you most often have the thing, no, you can't install anything from the internet. The only thing that you can do is you can provide us with a container that we can put on the machine, and then you can use whatever you have installed in that container to analyze the data. And that's in research, I think, the most common thing where it's really needed to use containers. It's also possible to install software into a file instead of into your computer. You essentially transfer the file. This is a somewhat executable in its own right. If you have an execution environment, so Docker, Podman, Obtainer, or anything. There are some drawbacks to containers, and one thing is that containers can hide complexity and hide problems that are never solved because we are just hiding that in the container, and that should realistically be solved because they are a problem. otherwise they wouldn't be hidden. So if the installation is so complex, then yeah, maybe it might be better to get the installation a bit more easily done, if possible, than in contrast to just providing a container. You can get into the, well, from works on my machine works only in this container problem, because if a container is not recreatable anymore, because it has some software that is not available anymore, yeah, it works in the container, but it doesn't work anywhere else. Doesn't make thing, well, at least it works somewhere, but it's still a bit problematic. They can be difficult to modify. So if you are in the situation that it works only in this container, then starting to modify that container and modifying the code that's in that container can be a pain. And container images can become quite large. We are talking about easily having things like 10, 20 gigabyte container files very, very quickly. So, and like with any software, if you have if you want to install or use a container, not all images can be trusted. Be sure where you get the image from. Don't just take anything, especially if you're using Docker, because containers on tenancy run with administrative privileges. So especially in Docker. So if you run something in a container, it essentially has admin rights on your machine. That's somewhat overcome on HPC system with tools like Aptainer or also Podman in non-root mode, which run differently, but on most workstations that run Docker, yep, you have a tool that essentially can do anything and runs on your system as root. So be careful what kind of containers you are using. So since exactly that problem that Docker is needs a root for installation, we will do the exercise here as a demo, because creating this the first exercise is something that you can have a quick look for 5 minutes as to how reproducible you think this is. And the second example I will demo so that you see where things can be useful, or how containers can be useful. So let's have a look for 5 minutes at this this time travel exercise. It's essentially about writing down what you notice with this Docker container, how reproducible that is, how good the Docker file is, or in this case the singularity file, as in specifying what goes in there, and if we can reproduce this just based on the Docker on the singularity definition file. Okay, see you back at 22, and then we are probably also quickly getting to the wrap up. And welcome back. So to quickly go over what the file has, I think the biggest issue, if you really want to reproduce this one, is that we have a latest here, which essentially means that this is some version. There's also the copying of local files that specifically say in some folder that's not in the same folder. So this could be from anywhere, and we don't even know if this is part of the repository itself or from somewhere else. So these are the two biggest flags in here that make reproduction somewhat difficult. I will quickly show you one thing where containers come in handy, and that is, for example, running an RStudio server. And I've already started it with Docker run. I don't have RStudio on my machine normally, because I rarely work with R nowadays. But like this, I can essentially get an online RStudio and have RStudio loaded and can run my R stuff. And if I have something that says it needs R 3.3 or whatever, or some older R version, I can specify which version I want by simply changing my Docker run command. And that's quite convenient just to get things to run, just to try things out. So as I mentioned, containers are quite useful in helping setting up complex systems and complex setups for specific software, and they can help you isolating things for testing stuff without messing up your own computing environment, your own system. So you don't need to install more complex things and thereby put trash into your system that you actually don't want to have in there. So where to go from here? Well, we've mentioned a lot of different things in this lecture, and I just want to come back to what Ina said in the beginning. Don't get stressed with these. It's not you have to use this all the time. We wanted to present you tools that exist, and we wanted to give you something that helps in reproducing things, that helps in making you be able to come back to your code and reuse it. Because this is, yeah, something that's quite important for you and for people that want to use your code. As for the workflow tools, as also mentioned in the lecture, probably in a lot of situations, they are not really needed. But if the workflows that you need to run become more complex, or you start continuously collecting data, they become more and more useful, and you might really want to think about starting to build a workflow in a workflow tool and not just in a script. Containers, they are sometimes amazing and sometimes really annoying because it's another level of complexity that you need to understand and that you need to be able to run. But on the other hand, sometimes you just can't get around using containers because the situation requires it, or it's so difficult to get something to run otherwise that the container complexity is a lot simpler. And you can run tools, Linux tools on your Windows or on your Mac that weren't easily runnable otherwise. It might allow you to have a lot more easy installation instructions, and yeah, and you get a fully configured environment. So I think what we want to really stress that is something that's useful for every project is having a clear directory and file structure, sticking to it and keeping it up to date. So not just having the structure, but also filling the structure with life. Record your workflow in a script and write it down in a script so that once someone else wants to do it, they can run a script and they can get get the results that you present.
Or also, if I may interject, I mean, workflow, if you have to have any other manipulation steps and you have to modify data and you maybe are not using code for that, which is always the best idea. But if you can't automate certain steps, also then write down a workflow that details those steps. So it doesn't have to be in a workflow management tool. It doesn't have to be a script, but it has to be documented what to do in which order. I think that's the important thing to note.
For me, one very, very, very important point is create a dependency list and keep it updated. Optimally do it in an environment file, but keep a list of the dependencies with versions that you're using. And personally, if I would be running something in a conda environment nowadays and publish that, I would provide the full export and probably the from history version, because that's what I installed and this is what I got, kind of. So you can follow the exact steps that I did, which might not lead to the same results, but you can also look into, okay, what has now changed between what he was doing and what I am doing now.
And you can always take the from history export and populate it with additional version information. So in the example, we had NumPy without a version, but of course you can take that from your full environment export and add the versions for the major packages in there.
And finally, if you at least consider that someone wants to reproduce your work, and hopefully people will, and anything that you can do to make their life easier and your life, very likely actually your life, if you build on your previous work, is really helping yourself and others. There's a lot of additional further reading that you can have a look into. And I think with that, I would give the head over to Enrico for some final words.
Yes, thank you, Thomas. So we are perfect on time because we have 1 minute left with our day 4 of CodeRefinery. At the bottom of the notes document, maybe if Jarno could switch to the notes document,
Yes.
we have this feedback. So if you click on the notes document and edit, you can add on the top, there's a poll where you can specify if it was too fast, too slow, and so on. And I can see already some people are answering. And in general, something good, something to improve, and any other feedback or questions. I think more or less we have covered everything, and we try to give useful answers, hopefully, to the notes document. So we are perfect on time, unless there's anything else that we should discuss. Ina, Thomas?
Not from
No.
my side.
All right. So thank you again so much to Ina and to Thomas for being instructors of day 4. And we will meet again next week for day 5, where we will kind of continue on this same topics, but more related to the collaborative side of things, when you need to basically agree with others, whether they are collaborators or stranger, how you will work together on a specific project or on a specific software. And so thank you again for the feedback, and see you in 7 days. Bye bye.
Bye.